Welcome to our webinar Basics of Protection. These sessions are made for those who start working or who are new in the field of protection and where a solid understanding of relay protection for distribution and transmission grids is essential. My name is Gerd Einsiedler and I'm happy to guide you through this second session of the webinar. Some of you might already know me. I have been working in protection and automation for nearly 30 years. Since September 2023, I am part of Siemens Power Academy in Nuremberg as a certified trainer for protection. And today I'm introducing you to the basics of protection lectures. Which protection principles do we use? What is the earth current? What are primary and secondary values? And since we receive one question rather often, yes, we will record the webinar and make the recording and the slides available to all registered participants. If you already joined one of our last webinars, you already know the Q&A field in this application. Please type in your questions to the presenter in the question field. We will answer your question during the dedicated Q&A session after this series on 21st of June. In addition to me reading aloud your questions, you could also chat with our experts in the background. And please be aware of the following limitation. The chat is available in live mode only. Q&A questions will be answered via email if not managed during the live session. And just in case you are in full screen mode, press Escape to see the Q&A and chat box. And now, let me introduce our expert, Prof.Dr Lemmer. Siegfried Lemmer graduated and received his PhD at RWTH University. He joined Siemens in 1986. For many years he was head of the product lifecycle management for protection, where he was deeply involved in the design of CPROTEC 4 and CPROTEC 5 relay families. Within a master course of power engineering at Brandenburg University of Technology Cottbus-Senftenberg, he presented lectures about protection for nearly 2 decades. In 2016, he retired from Siemens Life, but continued his university lectures. Siegfried, and now we are curious to learn more about the basics of protection technology. The stage is yours.
Which protection principles are available to detect short circuits? Let's look at this picture. Imagine we have a line and we have a protection relay, maybe on both ends of the line. They can measure the voltage and the current. And now, how can we detect that there is a short circuit on the line? And there are basically 3 principles available to do that. One is just looking at the current. It's quite obvious. If you have high current, it looks like a short circuit. That means the amount of current is an indication for a short circuit. And protection based on current, on only the current, is called overcurrent protection. We will look at that a bit more in detail later on. The next one I would like to mention is protection which is based on the impedance. That means we measure the impedance. To get the impedance, we have to measure the voltage and the current. And if we divide the voltage by the current, we get the impedance. And we will also see, based on the impedance, we can make a decision, is there a short circuit on the line or not? And protection based on the impedance is normally not called impedance protection, it is called distance protection, because the impedance is somehow a criterion for the distance of the fault. And the third principle is based on a current difference. That means we measure the current at 2 different locations and compare them and from that we try to find out, is there a fault on the line or not. And that principle is called the current differential protection. That means we have three different principles: overcurrent principle, distance principle based on the impedance, and the current differential to detect short circuits. I mentioned already in the beginning, we have also other types of faults, and to detect them, we need other principles. We can look at the voltage. We have to detect over voltages, under voltages, also the rate of change of the voltage, and the current is sometimes required. We can measure the power, apparent power or real power, and also the frequency is used as a criterion, and also the rate of change of frequency. Maybe the frequency, for instance, is often used for load shedding. You may know that normally the frequency is very close to nominal frequency, 50 Hertz or 60 Hertz. And if the frequency goes down, it's an indication that there's a lack of power in the system. And so what we often have in the systems is that we do, if we see the frequency goes down or we have a certain rate of change of frequency, we disconnect loads to stabilize the system. So these criteria here on the bottom are used to detect other faults. We will now in the next slides focus on the detection of short circuits, and we will start with overcurrent protection. That means our device only measures the current, and the job of the device is now to detect, is there a fault, a short circuit on the line or not? How can this be done? Imagine we have a certain range of currents, and what I indicate here in green is the normal operation. That means in normal operation we measure a current between 0 on the left-hand side up to a maximum load current. And then we have a range of short circuit currents. Typically, when you engineer your substation, you calculate the maximum short circuit current which may occur. That is always required to dimension the cross-section, for instance, of the cable. That is the maximum current at the right-hand side, but we are of course not interested only in short circuits with the maximum current. We must also take into account short circuits where lower short circuit currents are flowing, because there is some fault resistance involved, or not all generators are operating, or whatever. And with these considerations, we end up with a minimum short circuit current we want to catch. And if we now see that we have a gap, as in this diagram, between the maximum load current and the minimum short circuit current, then we can make a setting somewhere in between and can say, okay, in this gap I define a limit, and as long as the current is below this limit, I consider this as normal operation, and as soon as the current is above that limit, I consider that as a short circuit and will react on that. Important thing in this context is, what is the maximum load current? And that is in many cases not so obvious. Imagine you are behind the transformer, then you can say, okay, the maximum load current is the nominal current of the transformer. But is that okay? Imagine you can overload a transformer. That means you can have cases where you have a short overload, and if you set your limit directly to the rated current of a transformer, as soon as we have a slight overload, our protection will see, oh, it looks like a short circuit and will trip. And that's not good. That means you must make up your mind what is really the maximum current you will see without a short circuit. And that is often not that easy. Remember, for instance, one critical situation. You have an overcurrent protection, and behind this protection, or this protection looks into a distribution system which supplies a number of streets in your city. And you have this thing out of operation for maintenance or after a blackout or whatever, and you are in a city with very hot temperatures. That means you have a lot of aircon. And your maintenance or repair work takes 2, 3, 4 hours, sun is shining, all the buildings heat up, and now you reconnect power. You are happy your repair work is done, you reconnect power, and then at the moment you reconnect power, all the air cons start running at the same time, and you get really a high current in the beginning, which slows then down a bit. But if now your setting is too low, with this high current you come above your setting and you will trip again. That means you won't get that system into operation again. And that means if you think about the maximum load current, you must take into account such considerations and must add a certain security margin there that you don't get this problem. The other thing you also have to take into account there is you have to look into the future, because you calculate your setting when you install the device, but you don't want to reconsider the setting every month. That means you must have a setting which is also valid after some years when maybe the system has been extended later on. Also, that means you have to look a little bit in the future. But important thing here is what you can see from this diagram. You can only catch faults, you can only detect faults where the current of the fault is higher than this maximum load current plus a certain security margin. With that, you cannot detect faults with a very low current. That's not possible with this principle. That means if that can be applied, we can detect fault. But remember, detection of fault is one story. We also have to be selective. Detection of faults means the current is that high, there must be a short circuit, but we still do not yet have the decision, is the short circuit on our own line or is it on the next line? That means the topic of selectivity is not included here. We will see later on in the second part of this webinar that we need some time delays to get selectivity. But basically, this principle is widely applied. You have it in fuses, and here in our field, you have it in protection relays, overcurrent protection, and there we have to distinguish between two different types, inverse time overcurrent protection and definite time overcurrent protection. We will look now a little bit into these different types, how they work. So how does an overcurrent protection look like? Let us start with the three phases of our protected line or cable. They are shown here. And now we measure the current, only the current, by using this rate current transformer, and we connect this current transformer to our protection relay. I draw here parts of a protection device. You see here an input transformer. That's a measuring input, the connection point where the relay measures the current which comes from our current transformers. Then we have a shunt, A to D conversion, some algorithms who calculate the current. And then somewhere in the digital system, we have the amount of current we see. And with this current, we go into this blue block. And that gives us a signal if the current is above our threshold limit we just discussed in the previous slide. And it also takes a time delay. That means the behavior of the relay is mainly affected by this blue block. And in this block, the user has to do some settings to adapt that to his system. If the block issues a signal, it then goes to the circuit breaker and will trip. This shows just one phase. We always have three-phase system. That means we must multiply that by 3. And we do here on the right-hand side an OR connection. That means if we see a fault conditions in at least one of the 3 phases, we will issue a trip command so that we can detect all types of fault. Now let's look a little bit more into these blue boxes. What is inside there? And that is shown on the next slide. As I already mentioned, we have 2 types of overcurrent protection, and they can be distinguished by looking into these boxes. That means these boxes have a different characteristic. That means a delay time depending on the current they detect. And this characteristic is normally plotted in such a diagram that you see here on the right side. The horizontal axis is the current we measure, and the vertical axis is the delay time. And what you see here is a certain range of current from 0 to the setting value. This is the setting value. This is the load area. You see that would be the nominal current, maybe of our transformer or whatever. We have a certain security margin. And as long as the currents are somehow in this load area, the trip time is infinite. That means we have no trip. As soon as we are above the setting limit, then we start our timer, and then we will issue a trip if this condition remains there for a given time. That means a time which is given by the user. That means this characteristic has basically 2 setting values. One is the current setting and one is the timer setting. The current setting is derived from the considerations I did on the previous slide. Above maximum load current plus a certain security margin. The timer setting comes from the selectivity considerations we will discuss later on. This type of protection with this defined time as soon as we are above a limit is called definite time overcurrent protection. Another alternative for this block is the so-called inverse time overcurrent protection. There you have, first of all, a similar situation. That means as long as you are in the load current area, you have no trip. Trip time is infinite. As soon as you are above a set value, it means, yes, I detect a short circuit, but then the trip time depends on the amount of current we detect. That means if we are slightly above our limit, we trip with a longer delay time. If we have very high current, we trip with a shorter delay time. That's a typical characteristic you may know from fuses. This is called inverse time characteristic, and we will show in a separate chapter how you can get selectivity by applying these concepts. So either using definite time or inverse time characteristics. That was the overcurrent protection. So remember, second principle, distance protection based on impedance. How does that work? This picture shows just an extract from a meshed system. And of course, in a meshed system, on beginning and end of every line, you have a protection relay with a circuit breaker. What I show here is only one of these protection relays to explain the principle. This protection relay measures voltage and current and calculates the impedance. And now it compares the measured impedance with the impedance of the line. And based on this comparison, it can decide, like in the upper part, if the short circuit is on the line, the measured impedance from the relay to the fault is smaller than the impedance of the line. And if you look at the lower part, where the short circuit is on the next line, it measures a larger impedance, an impedance which is higher than the impedance of the line. Then it says, okay, I see a short circuit somewhere, but it's not on my line. That means based on this comparison, measured impedance against impedance of the line, we can get a decision, fault on the line or fault somewhere else. That means with this, we can get selectivity without any delay times. And that is the advantage of distance protection. I already mentioned it's called distance protection, although it is based on an impedance measurement. That means we also have this blue block in our device. But the content is a bit different. We need as input quantity the voltage and the current so that we can calculate the impedance. You may know the impedance are treated as complex values, unfortunately. That means we have a resistive part, which is drawn in the horizontal axis, and we have the so-called reactive part, which is drawn in the vertical axis. That means if we do one measurement, we get one measured point in this so-called complex impedance plane. And to make the decision, is it on the line or not, we define an area in the impedance plane, and as soon as we measure an operating point inside this green area, we issue a trip signal. That is the principle in distance protection. Third criterion was the differential protection. What is the idea there? Remember, you have a simple line. I indicate here the three phases. I first of all focus just on one phase. You measure the current at both ends of the line, in this case indicated as I1 and I2. Normally, current flowing into the line is calculated as positive. That means if we have in this picture here a current flow from left to right, let's assume 100 amps, I1 would be 100 amps and I2 would be minus 100 amps because it flows against the indicated direction. That means in normal operating state, the sum of these two currents is 0. If we now have a short circuit on this phase, that means a connection from the phase to ground or from this phase to another phase, it disturbs our equation. And that means the sum of the two current is no longer equal to 0 because part of the current flows another way. That means we can use the sum of the measured currents as a good indication, is there a short circuit on the device or not. And that is the differential criterion. In this case, I introduced it just for a single line with two measurements. You can also use it for a multi-terminal line because the principle remains the same. And that is indicated here. That means you draw a circle around the protected zone. The protected zone can be a line, a transformer, a bus bar. You measure all the currents and you sum up the currents. Do that individually for all three phases. And in normal operation, this sum should be 0. And if this sum of the three currents, we call this sum the differential current, is unequal to 0, then it is an indication that there is a fault on the protected line. You may realize in this context, just comparing a measured current with 0 and saying, okay, as soon as it is unequal to 0, there is a fault, is not a good idea. Of course, in real life, we must always compare it with a certain tolerance, with a certain threshold value. That means finally the differential criterion is we calculate the differential current and compare it with a certain threshold. And that is a little bit the tricky thing in differential protection, to define the correct threshold values. But the principle is a very simple thing. And we can apply it, first of all, to lines, as indicated here. We have a line from A to B. We want to protect this line. We want to detect short circuits there. What do we have to do? We have to install a protection relay on both ends. That means one protection relay can measure the I1, the other protection relay can measure the I2, and now, of course, they have to exchange their information because we want to calculate the differential current I1 plus I2, and that's only possible if they exchange their measurements. That means a differential protection, a differential line protection always needs communication between the two or even three devices if we have a three-terminal line. And this communication, and that is important, is part of the protection system. It must be a reliable communication, because as soon as the communication fails or something goes wrong there, this protection doesn't work any longer. Communication is part of the protection. And you can imagine in this field, there's a lot of development going on at the moment. This principle of differential protection is already a very old principle. But nowadays, a lot of development work is going on in the field of communication, so that a lot of development is done there. For instance, discussing the question, can we use a company communication system for this data exchange? What about cybersecurity issues? Is it possible to hack into our devices if somebody gets access to this communication, and so on? That means beside these original really basic protection issues, you get a lot of other issues to be considered in this context. That is the application of the line protection principle, of the differential protection principle to line protection. The next area of application would be to apply that for a transformer. Then we don't need this communication thing because we are within one substation. We can measure the current on both ends of the transformer. But now we have to take into account a few other things, because on a line it's easy. If we have 100 amp flowing into the line, there should be 100 amp flowing out of the line on the other side. Of course, in a transformer, it's a bit different. Transformer has a winding ratio. That means if there is 100 amp flowing into the transformer, on the other side, we have a different current. That means we must take that into account to apply the winding ratio. And it's not only the ratio. If you look at a three-phase power transformer, that normally has, depending on the connection of the windings, has a phase shift between one side and the other side. And that also means if we compare the current on one side to the current in the same phase on the other side, we must take into account this phase shift resulting from the connection of the windings. And we also have to think about what happens if we energize the transformer and we have an inrush there. That means the principle, the differential protection principle, can be applied to transformers, also to motors and generators, but we have to take into account a few things to make it applicable in reality. And the third area of application is the busbar protection. Busbar protection, it looks pretty easy. Well, we have a busbar, we have in this case 5 outgoing feeders, and we just measure the currents and sum that up. Always separately for the 3 phases. Often these substations don't unfortunately look that easy. For that reason, I would like to show this example with a double busbar substation. You see here 4 outgoing feeders, double busbar, and every feeder has 1 circuit breaker, 1 current transformer, and every feeder can either be connected to busbar A or to busbar B, depending on the position of these isolators. Or even both isolators are closed in special situations. And of course, we want to apply the differential principle separately for both busbars. That means we want to calculate the differential current for busbar A and the differential current for busbar B separately. And to do that in a proper way, we must take into account the position of all these disconnectors here. That means we must combine the topology information, position of disconnector, with the measurement to apply the principle. That looks pretty trivial in such a small system, but imagine you have a busbar, maybe you have a triple busbar, you have 20 feeders. That means you have a lot of wiring and you have a lot of contacts, and you must also make up your mind what is going to happen if one of these contacts are somehow dirty, defective, or whatever, and you get the wrong topology information. How does it disturb the measurement? Because then you may do a wrong assignment of a measured current to a busbar. And that makes the application of the differential principle a bit tricky in case of the busbar protection. And you must always have in mind, if something goes wrong in a line protection, you have a wrong trip, you lose 1 line in the system. It's not nice, but it will not be a very severe thing. If something goes wrong in a busbar protection, you lose the busbar, and that means you lose all lines connected to that busbar. That means with 1 wrong trip of a busbar protection, you may lose 10 lines in your system, and that can produce already a critical system state. So with this slide, we are through the 3 protection principles. And in the next chapter, we will look at a very strange thing. We will look at the earth current. So we come to the earth current chapter. And I would like to start with a very simple question. What is the earth current? Is it current flowing to Earth, in Earth, from Earth? And I found out it's a very difficult definition, so it makes sense to look at this earth current a little bit more in detail. And I would like to start this discussion with a symmetrical three-phase system. Let's assume we have a cable, we have load current flowing. That means the current in each phase is the same. What you sometimes hear is, yeah, in a symmetrical system, the sum of all currents is zero. So it's a little bit astonishing in this situation. So if you have, for instance, 100 amp flowing on every conductor, 100 amp plus 100 amp plus 100 amp are 300 amp, not equal zero. So why do we say the sum of the currents is zero? We do that because we have sine waves in a symmetrical system. That means the current IL1 has, for instance, this purple sine wave. The current in phase 2 has the orange sine wave. And in phase 3, we have the gray sine wave. We see here the range in this diagram is 20 milliseconds. That is exactly one period in a 50 Hertz system. The purple sine wave starts at zero with a zero crossing. The orange sine wave has its zero crossing nearly 7 milliseconds later. That is a phase shift of 120 degrees. And the gray curve has its zero crossing another 120 degrees later. That means these three currents in a symmetrical three-phase system have a phase shift of 120 degrees between them. As electrical engineers don't like to draw all the time these sine waves, it makes sense to use another way of indicating that. We draw the sine wave, but basically we only need the information of the amplitude of the sine wave and of the phase shift. And instead of drawing that, we just draw. Oh, sorry, I wanted to indicate one thing. Sum of the currents is zero. You can do that, you can indicate that in this diagram. You see, for instance, if you take this red instant here, you see in this case the gray current is zero. The orange current is minus 100 and something amp, and the purple current is plus 100 and something amps. That means the sum of the three currents in this case is really zero. And you can do that for all other instruments. You always find that the sum of the currents is zero. But let's come back to the drawing with arrows. What we often do in electrical engineering, instead of using these sine waves, we draw arrows. That means the length of the arrow, look at this purple arrow for instance, indicates the amplitude of the sine wave, and the angle of the arrow indicates the phase shift. And in this case, vertical means phase shift zero. Then you see the orange arrow has a phase shift of 120 degrees, and the gray arrow has another phase shift of 120 degrees. So that basically has these three arrows, has basically the same information as the diagram with the sine waves. And what you can see here, if you sum up these three arrows, you also see the sum is zero. the purple one, connect the orange one to that, connect the gray one to that, and you see you end up with 0. That means the interesting thing is, in a symmetrical load situation, the sum of the currents is 0, either doing it with these arrows or just summing up the instantaneous values here in the sine waves. That is one thing. Now let's come back to the earth current, and to do that I would first of all like to draw your attention on the upper part of this slide. This indicates a cable. That means you see here the 3 phases of the cable. On the bottom the ground, in blue the conductors, and again there we have a symmetrical load situation. There is this symmetrical current system flowing in the cable. Now let us assume this cable has a short circuit. There is a problem in the insulation. We have a short circuit here, and what is now going to happen? We will have a current flow on, in this case, phase 3, through phase 3, here to the cable shield, along the cable shield, and then somewhere to ground. Depending on the system situation, part of the current will also flow to the other side. That means you have a very distributed current flow in Earth. Let us look at a similar example for an overhead line that is indicated in the lower part. You see here a few towers. Every tower is grounded with a certain grounding resistance. You see here in blue the 3 phase conductors, and on top is the earth conductor I already mentioned in the beginning. The earth conductor is connected, directly connected to the tower. That means it gives an additional connection of all the towers. And now if we have a short circuit, maybe on the center tower, what is going to happen? You get this strange current flow. That means the current comes from both sides along the line to the short circuit point, and then part of the current flows from here directly into Earth, and another part of the fault current flows along the earth wire into the grounding of other towers on both sides. That means you see here, in case of an earth fault, the earth current is a very distributed thing. There is no one location where you really can measure something, and that makes the earth current sometimes a little bit strange. But let's come back to the question, what is now the earth current in this context? And the earth current is, first of all, just a definition thing. We define the earth current as the negative sum of the 3 phase currents. We just say the earth current is minus IL1 plus IL2 plus IL3. We don't say it's a current flowing anywhere. We say it's just, first of all, an artificial thing with this definition. Unfortunately, it sometimes also has different names. Some people call it ground current. I personally prefer residual current because it doesn't have this strong connection with Earth. But what is now the important fact for protection? The interesting thing for protection is that this earth current is in normal operating states. That means in operating states where we have no fault, this earth current is nearly zero. It's not exactly zero because we have some asymmetries in the system, but it's nearly zero. And in case of an earth fault, this earth current increases. And that means we can use the earth current as a very sensitive criterion to detect phase to ground faults. And always remember, phase to ground faults is the majority of the faults. And phase to ground faults are also those faults which tend to have higher fault resistances. No, imagine a tree falls into a distribution overhead line. You can have pretty high fault resistances. That means these are the cases where the fault currents can be pretty low, and it makes sense to have a better opportunity to detect them than we had it up to now when we only looked at the phase currents. If we want to use the earth current for protection, of course, we have to measure it somehow. Of course, theoretically, we can just measure the phase currents and can calculate it internally. What is often done in protection relays is shown here. This is a protection relay connected to the 3 current transformers on the cable or on the overhead line. And what I indicate here are the measuring inputs of the protection relay. We have 1 measuring input per phase. And then these 3 wires are connected here to a star point. And because you bring these 3 wires together, there you have then a location where you have the sum of the 3 currents. And we normally connect this sum of the 3 currents to a 4th measuring input. And this connection is called Holmgreen connection of a protection relay. And I would say that is a standard connection of a protection device. Of course, you could also save 1 measuring input. You could make the whole design a bit cheaper. You could say, as the earth current has this definition, negative sum of the phase currents, it's easy enough just to measure the phase currents and do the computation internally. Well, we have a microprocessor system, there's no problem to sum up the currents. The advantage is if you do this Holmgreen connection, you have a certain amount of redundancy in your data acquisition. That means you can measure the earth current by using this 4th measuring input to measure the sum of the 3 currents. And you can also do the computation internally, and then you can check, is that earth current you measure identical with the earth current you compute? And if you see a significant difference, it is an indication that something is wrong in your data acquisition. That means with this 4th measuring input, you get an additional redundancy in the measurement, and you can, with that, block the system if you detect something. Okay, that was the Holmgreen connection, which is widely used. Important thing here is you have some sensitivity limitations. Sometimes, for instance, in cases where the star point in the system is not grounded, the earth currents can become pretty low. That means you must be very sensitive. If you measure the earth current with this Holmgreen connection, you have the following problem. You measure through current transformers, and these current transformers may have measurement errors. And if all of them have the same measurement error, it's okay. But according to Murphy's law, normally the measurement errors go into the worst direction. You can have the situation that one current transformer, for instance, has a positive measurement error and another one has a negative measurement error. And that means you already get an earth current, even if you have an absolute symmetrical system, you get an earth current just resulting from the measurement errors of the current transformers. And this has to be taken into account. If you want to be more sensitive, there is a possibility, and that is indicated here in this diagram. Then we use a separate CT that is called core balance CT, and that is a CT which physically measures the current of the three phases. That means all three conductors go through the core of this current transformer, and with this installation you can get a much more sensitive measurements, and for that reason there are also sensitive measurement inputs available in the relay. So that was the question, how can we measure the earth current? Now let's come back to the question, what are we going to do with the earth current? How can we use the earth current for protection? Remember this picture I showed for the overcurrent protection? You have the normal operation range, you have the range of short circuits, and your setting is somewhere in between. And that means you cannot catch short circuits where the short circuit current is lower than your setting, and your setting must be above the maximum load current. That means you cannot catch short circuits which are, for instance, lower than or close to load current. Now, if we apply the same principle to the earth current, how does it look like? The point here is the green area becomes much smaller, because on the left-hand side, the green area is defined what is the maximum current we see under heavy load condition. If we look at the earth current, even with heavy load, we don't have much earth current. That means we must make up our mind only concerning the question, what is the maximum earth current we see resulting from unsymmetrical operation of the system plus CT errors, but that is much smaller. And that means we can make our setting to distinguish between normal operation and fault much lower than on the left-hand side. And that makes the earth current interesting for protection. That means with that we can detect earth faults where the fault current is lower than the load current. That would not be possible with this just phase measurement I show on the left-hand side. That means nearly all protection relays have, as shown here, a fourth measuring input and at least logic for the earth current. The upper three blue blocks, you have already seen them before. That is the characteristic, the settings for the phase. We add a measuring input for the earth current, Holmgreen connection or internal computation, as I discussed, and then we add here this yellow block, and this yellow block has maybe the same timer settings, but it has a different current setting. It can have a significantly lower current setting to react on earth faults. That means this would be the diagram, the total diagram of an overcurrent relay. That was the chapter about earth currents. I hope it's no longer a secret for you. And the next chapter will just be a very short chapter on primary and secondary quantities in protection. So let's look at primary and secondary in protection. What does that mean? Remember, our protection relays are connected to the system via current transformer and voltage transformers. That means we have current values in the line or in the cable, and this value is called the primary value of the current. And of course, we also have a voltage, for instance, between the conductor and ground, that is called the primary voltage. as discussed, we cannot connect that directly to our devices. We use current and voltage transformer. That means we also have a current which flows into the protection device, and that current is called the secondary current. And we also have a voltage which is seen or measured by the protection device that is called the secondary voltage. That means if we talk about electrical quantities, we must distinguish between primary side and secondary side. But it also means if we talk about settings, we can talk about settings in terms of primary values or settings in terms of secondary values. Just to illustrate that a little bit, I want to come back to the current transformers. You see here again a picture of a current transformer for distribution level. In this case, it has a current transformer ratio of 600 amp to 1 amp. That means the primary rated current is 600 amps. On the secondary side, we have 1 amp, and that is what goes into the protection relays. And in protection, traditionally, we have 2 standard nominal currents on the secondary side, and that is either 1 amp or 5 amp for this conventional type of transformers. There are other types also coming up, but still the big majority has these current transformers. And 1 amp and 5 amp are pretty high currents. Imagine these values are the current values for rated current, normal operation. And if you have a short circuit, you have, of course, much higher currents. And that is the reason if you look into our protection relays, that is a terminal block where the current is connected. Actually, you see 2 things. You see the terminal blocks where you connect the current are much bigger than the other terminal blocks. And the reason behind that is that they must be able to carry the high current. Nominal current 5 amp. Normally the devices have to be tested to withstand 100 amps, 100 times nominal current for 1 second. And that would mean 500 amps for 1 second. And you can imagine for that you need bigger screws, and of course you also need sufficient cross-section. What you also see here is you have phase 1, 2, 3, and you have the 4th pair of inputs for the Holmgreen connection or for a sensitive, for a core balance CT to connect it. That was the current transformer. On the voltage transformer side, we have typically, here's an example, 110 kilovolt divided by square root of 3 to 100 volt divided by square root of 3. Where does the square root of 3 come from? If you have a 100 kilovolt line, the 100 kilovolt is the voltage between the 2 phases. The voltage transformers are normally connected from phase to earth. That means the voltage they see in normal operation is in this case 110 kV divided by square root of 3. Same applies to the secondary side. It is normally something around 100 volt, also there divided by square root of 3. This voltage is also not quite standardized. 100 volt is a thing you often find, but you also may have 110 or even 125 volt. So that was the example, just the definition, what primary and secondary is. What does that now mean for protection? In all states where you calculate settings or where you deal with settings, it must be clear, are you talking about primary values or secondary values of setting? Normally, you start the calculation of setting values from a network calculation. You have to calculate load flow, you have to calculate short circuits, and the values you see there are primary values. Relay settings, as the relay measures behind current transformer and voltage transformer, are traditionally often treated as secondary values. That means on this way, from calculation of settings to bringing the settings into the relay, you must somewhere do the conversion from primary to secondary. With digital relays, that has become, of course, much easier, as a PC program can be used using the primary values. That means that can do the conversion. So part of this conversion can be assigned to a program or even to the relay itself. But nevertheless, you must be careful. And there are 2 points where, according to my experience, often problems occur. One thing is, if you talk about a setting of an overcurrent relay, it's very easy to see, is it a primary value or a setting or a secondary setting value. If somebody tells you the setting is 1000 amp, you know, okay, 1000 amp looks like a primary value. If he says the setting is 1.5 amps, you know it's a secondary value. That's easy. But also in distance protection, where the setting values are impedances, you have to do the conversion, taking into account the ratio of the voltage transformer and of the current transformer. And then it's not visible if somebody says the setting value is 5 ohms. The 5 ohms can be a primary value or a secondary value. It must be clear what it is. And I had a lot of occurrences where something went wrong in the protection, and the end of the story was that people mixed up between primary and secondary values. It is basically trivial, but sometimes problems happen at that point. And the other thing, the other location where you have to be careful is the question, what is going to happen if a relay is in operation and somebody has the idea to change the current transformer? That means to install a current transformer with a different ratio. That can happen because something has to be replaced or the substation is extended or whatever. Then you must make up your mind, because in this case, you have to change either the primary setting value or the secondary setting value, because they are connected with the ratio of the current transformer. And if you change that ratio, at least one of them has to change. And it must be very clear that you decide which one has to be changed and which one can remain constant. That was a short chapter about primary and secondary. And in the next chapter, we will start to build up a protection scheme for a feeder or a transformer feeder.
Thank you, Siegfried. That has been an interesting session with insights into the basics of protection technology. Dear auditorium, thanks a lot for your questions. We will answer these in the Q&A session on 21st of June. If questions come into your mind later, or you would like to go for more details, please visit our training platform at Siemens Power Academy. I'm sure you will find the right information and training. The access to the recording and the slides will be sent to all participants. Thank you very much for your active participation. It was a pleasure for me to guide you through the second session on basics of protection technology. In this session, we learned which protection principles we use, what earth current is, and what are primary and secondary values. I'm looking forward to meeting you soon in the third session of Basics of Protection on June the 6th, which is focusing on how do we build a protection scheme in part 1, reliability in protection, a difficult discussion. How do we build a protection scheme in part 2. And now stay safe and sound, take care and goodbye.